Hi everybody and welcome to the third video on molecular weight of the polymers. Well, you see the picture of this, you can call tractor in a road, in a highway, and what does it have to do with the molecular weight of the polymers? Well, let me start with what happens when polymers are dissolved in a solvent. Polymers do something weird when you dissolve them in a solvent. They make the solution viscose. You have seen this. Polymers are used as the thickeners in things like shampoo and even ice cream. This thickening effect can be used to estimate a polymer's molecular weight. But why do polymers make solutions to become more viscose? For one, polymers move very slowly, or we can say at least they move a lot more slowly than the small molecules of our medium. It makes sense when we say that the faster molecules in a liquid move, the more easily the liquid will flow. It is something obvious. But when we dissolve a polymer in a solvent, the slow motion of the polymers will make the solution, the whole solution, to become more viscose. But this is the question: if the polymers are slow, if their movement are slow, but why does the whole solution become viscose? This is a question. Do the polymers make the solvent molecules to move more slowly too? And if it is so, why and what is the reason? How is it going to happen? Well, the answer is yes. The answer is that when we dissolve the polymers in a solution, the solution becomes more viscose. Polymers are somehow pushy. It's not enough for them to just move slowly themselves. They feel like they must make the solvent molecules to move more slowly too. But how are the polymers going to impose their ways on the solvent molecules and making them to move more slowly? Just have a look at this picture. You see the big giant tractor which is moving slowly in the fast lane, and it slows down all the cars. You see all the cars behind that. If you consider this as a polymer which is moving in the medium, and these ones as the solution molecules, so because this polymer is moving slowly, it makes all of them to move slowly as well. So by getting in the way of the fast moving solvent molecules, the whole solution will become more slower and more viscose. Another reason is that polymer molecules do more than just blocking the motion of the small molecules. They also slow them down through the intermolecular forces. Just imagine if there are any attractive secondary interaction between the tractor and these cars. Okay? If there are these secondary interactions, between the polymer and the solvent molecules, the small solvent molecules that we have here can become bound to the polymer. So when it happens, they move with the polymer more or less, and of course they have to move at the polymer's slow speeds that we have here. It might help you to think of a polymer as a group of children that they are moving together. Okay, I want to give you an interesting explanation of the reason why these polymers are moving more slowly. Well, let's continue with this picture. I want to explain the reason why polymers move more slowly compared to the small, medium, and solution molecules. This is a fancy way of saying that polymers move more slowly than the small molecules do. Just imagine you are a first grade teacher and it's time to go to lunch, but your task is to get your kids from the classroom to the cafeteria without losing any of them, and to do so with minimal damage. You'll have to cover to get to the cafeteria, keeping them and hollering and bouncing this way and that. One way to put a stop to all this chaotic motion, to all the chaos that these children have, is to make all the kids join hands, to hold their hands when you are walking them to lunch. This won't be easy because as there's always going to be a lot of little boys, you see, like this little girl and these little boys, who are too macho to hold the hands of the girls that are next to them in line, and some, they are just insecure of their manhood to hold anyone's hands. They are shy. You see these? They are really shy and they don't hold the hands. But once you get all of them to do this, their ability to run around is severely limited. Once all the children hold their hands, their ability to run away will be limited. It is like a polymeric chain. We have a chain of the unimers, of the monomers bound together, just these children. Of course, their motion will still be chaotic, but the chain of the kids will curl like a snake this way and that way, when they go, but they are bound together. And as a result of that, the motion when you are moving to the restaurant, to the cafeteria, will be a lot slower. It's the same way with the molecules, with the polymers. A bunch of small molecules can move around a lot faster than the time that a lot of more molecules are bound together. When you tie the molecules together in a big long chain, they slow down. It's really simple. Just like kids, when they hold their hands, the ability to move will become, let's say, more and more slower. Well, These two explanations that I gave you about the reason why the molecules, the polymer molecules move slowly, and the reason why they are introduced into the medium, into the solution, and make the solution to become more viscous, will make us more ready in order to realize and understand the rest of the slides of the molecular weight and the importance of calculating the viscosity and the molecular weight of the polymers. Okay, now let's get into this picture. Just forget about the names of the microgel and the linear polymer, just consider the size that we have here, because we are going to talk about the size of the polymers and the molecular weight. Well, the question is that, okay, polymers make the solutions to become viscous, but what does all this have to do with the business of measuring the molecular weight? The thickening effect, the effect of becoming more viscous when you add the polymeric chains, helps you to estimate the molecular weight of your polymers because of a simple fact. And this fact is that the higher the molecular weight of your polymers are, the more viscous the polymer solution will be. This is reasonable. When a polymer has a higher molecular weight, it has a bigger hydrodynamic volume. I told you that the polymers will form the coils, and the size of the formed coils is directly proportional to the size, to the chain length, to the length of the polymer chains that you have. So when the chain length is bigger and the formed coil is bigger, the polymer molecule can block more motion of the solvent molecules. You remember this tractor that I showed you before? I mean that it can block off more lanes of the highway. And you might say that, okay, the bigger a polymer is, the stronger the secondary forces are. So it is stronger to bound the small molecules around itself and to prevent them from moving. So for most of the polymers, there's a definite relationship between the molecular weight and viscosity. So by measuring the viscosity, you can get the molecular weight. And that's just what I'm going to talk about, measuring the viscosity of a polymer solution.